All right, so we've gone over anatomy and physiology. We've talked about electrophysiology. Now let's discuss how do we measure that? Because if the heart is an electrical organ, there has to be a way for us to track that. So here we go. So the answer to that question is the electrocardiogram, known as either ECG or EKG. Why does the K exist? Well, basically that's the Greek spelling. When they originally invented this, it was electrocardiogram with a K. Nowadays we use C for cardia, so hence the reason we use ECG. Either one are appropriate, they're pretty much interchangeable. For me, I use ECG to describe your normal telemetry stuff, what we do day to day, and reserve EKG for the 12 lead rhythms that we do there. Again, either one are appropriate. So you'll see me interchanging those throughout. Important other fun things before I delve any further. The guy who invented this is Willem Einthoven, and he did it back in 1901. He's the one that refined the machine and the process. He actually got a Nobel Prize for it back in 1924. So literally for over 100 years we've been doing EKGs on people to try and figure out how the heart works from an electrical standpoint. And in that time, here's what we've learned. All that you can do with an EKG is identify rhythm disturbances and conduction disturbances. You cannot identify if there's a specific structural problem or if there's a perfusion issue, because those are mechanical. Structure and perfusion, that's your blood pressure, your pulses, and even your patient's level of consciousness. And the reason I take the time to point this out is because you can't just rely on what you see on the monitor. You have to put eyes on your patient. Look at your patient, get their vital signs, things like that, and see what kind of shape they're in. That's what you have to do beyond just measuring the electrical activity of the heart. All right, so I am taking the time right now to say this because it is the absolute foundation of being able to read ECGs and EKGs. You have to put the stickers, the leads on correctly and well in order to get a good signal. Otherwise, it's like trying to watch a high resolution video on your mobile device when you've got a bad Wi-Fi connection. Like you're going to be skipping all over the place. It's going to be blurry. It's just not going to work right. So the absolute most important things you need to do whenever you're placing them from the very start is, of course, removing any dirt. It's kind of a given. Clip the hair. Don't shave them, but get the clippers out. Get that chest hair out of the way. It's just going to make a big difference. Don't clean with alcohol pads unless they have like really oily skin. You don't want to mess with that because then the skin gets dry and it doesn't work well. If you have one of those individuals that has really dry, flaky skin, some older folks tend to have a little bit of that layer built up, you may want to actually abrade the skin slightly. So a lot of modern telemetry patches actually have this little strip on the back side of the sticker, and it's like an emery board. That's what it's for. You're actually supposed to just gently sand off the skin, for lack of a better phrase, wipe that clean, and then put the sticker on. It'll greatly improve your connection, it'll improve your signal, cut down on artifact, and just make life overall easier. Back in the day, gel electrodes didn't have gel on them, but nowadays most of them do. If you really want to get creative, you can use the ultrasound gel like you do for bladder scans, put a little dollop of that on there, and that might actually enhance your signal. Okay, so this is what's known as standard 5-lead electrode layout. This is one of the original ones, and it's pretty much what all modern electrophysiology and ECG readings have been based on. And the idea is this: you put 5 stickers on your patient. So you start with your white one over here, and that is going to be on the right side, your midclavicular line, and second intercostal space, so right up here. So that's going to be your white. Now you want clouds over grass, correct? So grass would be your green one down here. And so your green lead is going to be right there at the tip of the rib cage. Is actually a great place to put it, especially if you have an obese patient where their stomach's really rounded. Putting it at the tip of the rib cage is a really great spot. And the idea is you want to have a nice straight line down. You want to have those in line with one another. Now on the opposite side of the chest, you'll have your black one up here with your mid-clavicular line, and that's going to be your left arm. And notice these letters now. You've got your right arm, left arm. Directly below your black one, of course, it's smoke over fire, so your red one goes down here, again at the tip of the rib cage, creating a straight line down. So if you've laid these out correctly, your green one will be across from your red, and your white will be across from your black, creating a rectangle. And that's what's necessary for a standard 5-lead to function well, is to create that perfect box. Last but not least, of course, you have your brown lead, and your brown lead is supposed to go 4th intercostal space, just to the right of the sternal border. You actually don't want it on the sternum. You want it just off to the right side, right in between the bones there, right on the muscle. That's a standard 5-lead. Now, we at our facility use something called EASI mode. There's a number of facilities across the country that do that. And EASI mode is essentially an algorithm that takes 5 leads placed on a patient's chest and runs it through this algorithm and is able to create a non-diagnostic 12 lead using only 5. And that's why it's non-diagnostic, because you don't have 12 leads, you only have 5 in place. But it works really, really well. It's an older technology. It's been around 15, 20 years, so it's not something terribly new. But what is absolutely imperative is that we put the leads in exactly the right spots so that the algorithm can do its calculations properly. And when we're doing this one, we actually start with the brown lead. So your brown lead, which is this one right here, is at the level of the sternum. I actually try and find their xiphoid process and put it just above that. Once you have your brown lead in place, of course, you can put your black lead right here at the top of the sternum, just below the clavicles where they meet. And so that is your black lead. Now for your red and your white lead, you want both of those to be directly across from the brown, as if you're wrapping a belt around the patient. And then they don't go in the front, they actually go out here on the side of the rib cage. They're actually in your mid-axillary line. And I will underline that there. Now your red is still on the right side, or sorry, your red is still on the left side of the patient, and your white is still on the right side. And what that does is essentially create an upside down T, and that's what the algorithm is able to use to come up with its representations. Last but not least, you've got your green lead, and this green lead actually needs to be at or around the level of the umbilicus, so and actually a great distance away from that white lead. You don't want them too close together, otherwise it'll throw things off. That is the straightforward part of how EASI mode works and how you're supposed to place them properly to get the best signal. Why do we even bother doing it this way, though? Well, the reason is this. Being able to have a continuous non-diagnostic 12 lead gives us early warning alarms for a patient who may be having, if they've got chest pain, or if they're actually here for an MI or recently had a PTCI, a coronary intervention. We want to be able to catch if they have any ST changes in one of those V leads. More on that in the 12 lead course. All right, so this is a basic EKG grid, EKG paper. This is very, very standard. Pretty much all of them work exactly this way. And the idea is this. You have time along the bottom traveling this direction, and voltage traveling up. So the time portion of it, each small box, so we tend to measure this in seconds. And so each small box right here is worth 0.04 seconds. Now you'll see each small box is contained in a larger cube. So in that larger cube you actually have 5 small boxes. So 5 times 0.04 equals 0.20 seconds, so that each large box is worth 0.2 seconds. Now if you really want to do fun math, and we'll start here and we'll say 1 large box, 2, 3, 4, 5. So 5 large boxes across here. We'll take 5 times 0.2 equals 1 second. So for every 5 large boxes, you have 1 second across the paper. And that's just the general idea of how we do timekeeping. And so when we do any measurements on any types of rhythms, we talk about how many seconds long it is and things like that. Well, you can also just communicate and say small boxes, assuming that everyone knows you multiply times 0.04 to make sense out of that. I will apologize in advance. I tend to drop off the point whatever, so instead of saying 0.12, sometimes I'll just say 12. And hopefully you'll get used to that as this goes on. Now the next portion is going to be your voltage, and that's essentially your electricity. And we measure that in millimeters because each one of these boxes is 1 millimeter squared, so 1 millimeter tall, 1 millimeter long. And so we measure voltage vertically. Now, to make the most sense out of this, I'll say this. So when there's no electricity flowing, you actually have nothing going on. And what the paper does and what EKGs do is measure how much electricity total at that very instant in time is flowing in any one direction, whether it's flowing towards the electrode, making it positive, or if the electricity is flowing the opposite direction, which makes it negative. But it just adds up how much electricity it sees, plain and simple. So if we're going along and then it measures a total positive electricity at that moment coming towards it, and then less electricity the second later, you wind up getting this little arch. And then if it measures nothing, you see nothing. And then all of a sudden, if it measures a lot of electricity moving towards it, every millisecond, just more and more, and then it measures a little less, and then a little less, and then a little less. Now the electricity is actually flowing away from it, quite a bit actually. Well, the electricity is still flowing away from it, but then there was less than a second ago. And it comes up, and now no electricity, no electricity. Well, now it's measuring more, and it's kind of traveling towards it, but not nearly as much in one single instant. It's a little bit less. And then no electricity flowing. That is how you create an EKG rhythm, how you create a strip. And so you can see how, granted, my numbers are not perfect by any stretch of the imagination, but it demonstrates the idea that then if I have anything that looks different, I can easily say the electricity flowed away, came back to nothing, flowed towards it, less, now the electricity is flowing away, comes back, a little more electricity than is our baseline, and then there was some, and then back down to 0 again. Those are the ideas behind it. It's just an instantaneous measurement of all the electricity and whichever direction it's flowing. So let's find out some names for all of these waves. Okay, so this is a basic standard EKG complex as seen from lead 2. So what we start out with is our isoelectric line. And this serves as a baseline for everything, saying that no electricity is flowing one direction or the other. The first thing that you should encounter from the isoelectric line is going to be your P wave, and that's going to be upright. After your P wave, you're actually going to have this little segment here along the isoelectric line that is nice and flat. Following this flat segment after the P wave, you're going to encounter your QRS. And so a Q wave is down, the first downward wave following the flat line, following the P wave. But Q wave goes down, followed by an R wave, which goes up, and then the R wave should be followed by an S wave. We'll talk some more about the different combinations here in a bit, but the idea is that QRS follows the P wave and its flat spot. And after your S wave, you have another isoelectric line, which is then followed by the T wave. So this is your standard P, Q, R, S, T waves. Now there's a few other names that we need to go over, and so this section here that's in yellow is known as the PRI, also known as the PR interval. And that's really important because a lot of rhythms are determined or named based on how long that is. And I'll come back to that in a second. Your next section here is what's in red, which is just simply known as the QRS. Following the QRS, the question is, well, when does the S wave stop? When does it turn into something else? Well, at this little point right here, where the S wave flattens out and turns into the isoelectric line, that's what's known as the J point. And more importantly, this section here, from the end of the S wave until the start of the T wave, is known as the ST segment. And that's important for its own set of reasons as well. Last but not least, there's a larger one, and so I'll just kind of follow this line down and say from here all the way over to here where the T wave ends, and I'm just going to trace this down to about here. This from here to here is known as your QT interval, which is the entire length from the start of the Q wave until the end of the T wave. Measuring and recognizing specific changes in these waveforms will help you identify specific arrhythmias. In fact, the words we use to describe arrhythmias are based on a lot of these measurements. So we'll just do a quick little walkthrough in terms of that. So your P wave should be upright in lead 2. It should be nice, kind of domed in the shape that you see right there. Now the PR interval should have a measurement of 0.12 seconds all the way up to 0.20. Anything smaller or larger than that is a sign that there's an arrhythmia involved, some kind of conduction problem. Underline that. Your next one is going to be, of course, your QRS. I'll underline this as well. Your QRS should be between 0.06, 0.12. I want to make note that it's physically impossible in adults to have a QRS that is less than 0.06. Just the physicality is not there. So if it looks any smaller than that, it's probably not, and it's just the way the lines are laid out that it's difficult to measure. But assume 0.06 to 0.12. Anything longer than that, and you've got a specific type of arrhythmia going on. Last but not least is going to be your QT interval. And your QT interval in a normal healthy adult should be anywhere in the range of 0.36 to 0.44. If it's longer than that, you've definitely got a problem. If it's more narrow than that, not necessarily an issue. We tend to be more concerned about when it's too long. Other important items I want to add. The QT interval can be stretched out by certain medications, things of that nature. Your J point can be very difficult to find sometimes, and there'll be some examples of that. And your ST segment, we use that when we're looking at MIs and other things like ischemia. But that's more for the 12 lead class, so just know that it exists. And now we'll move on. Now this one's patient movement, and this patient here actually is a combination of both. There is some muscle artifact from shivering, but also movement, and it's this section right over here. You can see how there's these larger undulations that, is really due to the patient moving around more than anything. And even this mess over here, you can see that it's just awful to tell with. So again, please don't put these in the chart if you don't have to, but keep in mind that this is normal. It's not an actual arrhythmia. So this is a pretty classic loose electrode strip. No one can do their job well with poor information, and this mess right through here really looks like one or more leads is barely even touching the patient, and it swings wildly loose. So you have to lay eyes on the patient. You have to check your leads. And what you're going to be looking at is you're going to check the chest hair, because it may not have been clipped, and so you need to remove that chest hair, replace the lead. Check replace any leads, if not all of them, to see if that corrects this issue. Check the inside of their gown. Sometimes the lead catches on the gown and the patient's body, so when they move around, it gets really bad, but then you walk in there, they sit still, and it looks fine. Another really good one is mobile tissue. And what do I mean by that? I mean, check their rib cage. Lots of patients tend to have some extra just tissue, adipose tissue skin on their sides of their rib cage that looks fine when they're sitting still, but as soon as they reach or move or change position in the bed, will completely throw everything off. So check those places, and it should help improve things for sure. In standard mode, identify which lead or leads is incorrectly placed. So which ones are not where they belong. And if we just walk through these, for standard mode, that red one is way too high. It needs to be lower, on the same level as the green one. Your black one needs to be moved over to the patient's left shoulder a little further out, similar to the way the white one is. The white one's absolutely correct. The green one is absolutely correct. But that brown one is on the wrong side of the sternum. It actually needs to be on the right side of the sternum, not on the left. So of those, it's black, brown, and red. All three of those are incorrectly placed. In EASI mode, identify which leads is or are incorrectly placed. So for EASI mode, which ones aren't right? Well, the red one actually is in the correct spot. The black one is wrong though. That black one needs to be centered just underneath the collarbone. So the black one needs to move. The white one is actually exactly where it needs to be, but that green one is way too close. That green needs to be down by the belly button, or the umbilicus, if you prefer to use that term instead. Your brown one is absolutely correct, and that's where it needs to be. So for this diagram, the black and the green leads are the two that need to be moved around. This question's a little bit longer, so it's on 2 separate slides just because the options are laid out, but I will go ahead and ask. To ensure high-quality monitoring of telemetry patients and make the telemetry tech's job easier, which sequence outlines the proper approach to evaluate and correct the problem displayed on this strip? So what kind of rhythm or problem are we looking at here? It's obviously obvious that we're dealing with a loose electrode. And so now the question is, how do you best address that? And I'm going to bounce back and forth between the 2 slides here. And so I'll just go ahead and put 1 here, and then I'll jump to the next one and say 2. So back to slide 1. Do we address this problem during the next set of rounds? Do we address it immediately? Do we just address it as soon as possible or as soon as possible? Well, ideally, it's just a loose electrode, and so you do have monitoring going on. So it's not emergent, so we can hold off for a little bit. So we probably don't need to do this immediately, so we can check that one off the list. And so now, do we just wait until the next time they put their call light on, or do we instead do this as soon as possible? Well, I don't know about you, but if we wait until the next time they put their call lights on, that may lead to, it could be an hour or more, and this could be a problem that would make the telemetry tech's job a lot more difficult. So in order to support our coworkers, we'd want to go sooner than later. So that pretty much takes off during rounds as an option, and we're down to C and D. Which of these is appropriate? So as you read through these, look and try and tell which one of them has all the components that you truly need. We enter the patient room for both of those. We visualize the condition of the patient because we always want to make sure that they're in good shape. We're going to check placement of all 5 leads, not just one of them and call it good. You need to check all 5 always. We're going to move any of them that are incorrectly placed, and that's extra important because if it's on and you just leave it, you're already there. You're doing the effort. You might as well take it to the next step and make sure everything's done as correctly as possible. Replace any stickers on all loose electrodes, and that's actually the same here that you replace. And last but not least, you either confirm at the bedside monitor if you have one, or with the telemetry tech that the problem's been corrected. Now that's different on D than here, where just wait for the telemetry tech to tell you if it didn't help. That kind of leaves a lot of questions and you're not sure if you did it right. You should always close the loop on your communications. Call back and ask, did that fix the problem? Because if it didn't, you're there and you can do the troubleshooting that needs done. So between these 2, I'm going to say D is the most correct sequence of events or proper approach to evaluate and correct the problem when you have a loose electrode like this.